In just a couple of seconds, Spain is about to get its first total solar eclipse in over 100 years, and we're here with NASA to film it from space. But we almost didn't do this video because it turns out there are a great couple videos on solar eclipses on YouTube, and we just thought we couldn't add anything. But then we started looking. Oh my God, that's insane. And it turned out, oh, I can't, I just gotta go watch this. That's insane.
So Henry, Amelia, and I still had some unanswered questions like, why is the Northern Hemisphere getting more total eclipses than the Southern Hemisphere? Why does the sun suddenly turn white only during pure totality? And how come we still haven't figured out what causes these elusive shadow bands on the ground?
Oh, that's so weird.
Okay, so we are on the way to Burgos, Spain, because it's gonna be right in the center of the moon's shadow, so perfect for totality. And we're also meeting up with NASA and a bunch of other science groups because they're launching a couple balloons up to the edge of space, so they will actually be filming the eclipse. And hopefully they can answer some of our questions. Vamos! Oh my God, it's getting occluded, oh no.
Angela?
Yes.
Oh, lovely to meet you. I'm Amelia.
Oh, so nice to meet you.
Yeah, this
Hi,
is
Ryder.
Ryder.
Nice to meet you, thanks for
Nice
having
to
us.
meet you.
I'm sorry, can I ask?
Yeah.
Are those total solar eclipses on your toes?
Yes. Totally geeking it up. Yeah.
Yeah. I guess first question right off the bat, how many eclipses have you seen?
So this will be my 4th eclipse and the 3rd total eclipse. There's lots of folks here who've seen many more than me, 8 or even as many as 12.
That's crazy. So how rare is it that Spain is getting 2 total solar eclipses in less than 12 months?
If you picked any random point on any place on the Earth, it's about every 300 years that the eclipse will repeat there. But then there are some places, you know, where there happens to be occurrences because there is kind of a pattern to the eclipses.
You can see one of those patterns if you map out the paths of all total solar eclipses between 2000 BCE and 3000 CE. Notice that the Northern Hemisphere consistently gets more eclipses, about 15% more than the Southern Hemisphere. Now, for there to be a total solar eclipse where the moon completely covers the sun, you want it to be bigger than the sun in the sky. Now, the biggest factor for that is the moon's elliptical orbit. Sometimes it's further from the Earth, sometimes closer. So over the course of the month, its apparent area increases by up to 30%. But the Earth's orbit around the sun is also elliptical. So from our point of view, the sun's area is about 7% smaller in July than it is in January, which means there's a higher chance of a total solar eclipse around July. But that's also when it's mostly the north half of Earth that is tilted towards the sun, the Northern Hemisphere summer, so that's where the total eclipses tend to fall. Now, the Southern Hemisphere is actually going to get more annular eclipses where the moon is slightly smaller than the sun, so you have this ring of sunlight around it, and that's because during the southern summer, the sun is actually closer. All of this is actually going to flip because the Earth precesses around its axis and its elliptical orbit also slowly shifts around the sun. In about 9,500 years, it will be the Southern Hemisphere that gets more total solar eclipses. Now, there is another interesting pattern that shows up when you look at all types of solar eclipses, including annular and partial ones too.
So I crunched some numbers, like 5,000 years of eclipses, and if you look at how many happen per year, there's never a year without some sort of solar eclipse, which kind of feels mind-boggling. You at least have to get 2, and sometimes you can get 5.
How would you get 5?
Yeah, I know. Let's check this out. So,
the moon's orbit is tilted about 5 degrees out of the Earth-Sun plane, so most times the moon passes in front of the sun, it's at the wrong height to cast a shadow on Earth, and that's why we don't get a solar eclipse every month. But there are these 2 nodes along the moon's orbit where it does actually cross the Earth-Sun plane. And throughout the year, both of these nodes are going to land nicely in between the Earth and the sun. This happens about 6 months apart, and it opens a window of around 34 days where solar eclipses become possible. And these are called eclipse seasons.
There's this huge window to get eclipses.
yeah. So as long as you get a new moon somewhere inside of this eclipse window, you get an eclipse. But it turns out you have to get at least one. The reason is the eclipse season is 34 days, but a new moon happens every 29.5 days.
Of course, yeah.
So you can't go through an eclipse season without the new moon happening at least once. However you roll the dice, it always has to land inside the eclipse season at least once.
So you always get 2 a year.
2 a year.
Great.
Yeah, right?
Now, if the new moon falls towards the middle of an eclipse season, it usually produces a total or an annular eclipse. And you can only fit one of those types of eclipses into a season, so you can get about 2 per year.
Yeah, that doesn't seem rare. Definitely not once in a lifetime.
Yeah, but it gets worse. Because if you also count partial eclipses, those happen more towards the edges. And because they happen towards the edges, you can get 2 in a single eclipse season, or you can get 4 a year.
But wait, then how do you get 5?
Yeah, the thing is, the eclipse seasons themselves also drift around the Earth's orbit. So if you start on January 1st and you get an eclipse really, really soon into the year, you can hit like a partial and then another partial. And then as you're moving, these eclipse seasons are shifting. So you get another one, and then you think you're done. But the eclipse season has actually already shifted into December, and then you get a final one. So you can get like up to 5.
Whoa.
Okay, wait, I realized I forgot to tell you my favorite fact out of this whole discussion. And that's that if you look at the eclipse season, when the eclipse happens, the solar eclipse here, and you rewind by about 2 weeks, you'll realize that now the Earth is in between the sun and the moon.
So you get a lunar eclipse.
So you get a lunar eclipse, which means every time there is a solar eclipse, it is accompanied by a lunar eclipse either 2 weeks before or after.
Oh, that's so cool.
Yeah, so there's one happening in 2 weeks.
Oh, amazing.
Yeah, it's really cool. I actually tried to find answers to this question, but if you look at time lapses taken during the eclipse, you'll see that the partial parts are usually like yellowish in color, and then the totality is white. Even if you Google on Google, you get like a little animation and it turns white. Yellow, and then it's white, and then it's yellow again. I could not find a satisfying scientific explanation for why that happens.
It's so bright, right? In order to take those time-lapse pictures, you have to put a filter in front of it. And so the most common with those filters, it's that kind of reddish orange color. So it's just the most common filter makes it that color because the sun is white, but then it's dim enough that we can look right at it during totality. And so you see white.
It's just the filter? Okay.
It's just the filter. Maybe I can show you where we're at.
Yeah, sure.
Where you can kind of get set up.
Hey.
We're a NASA-funded lab in Bozeman, Montana, and this is an extension of what's called the Nationwide Eclipse Ballooning Project. So we studied the 2023 and 2024 eclipse. So we have 2 teams in Reykjavik, Iceland, and we have 3 teams here in Spain. The Iceland teams are launching essentially weather balloons, radiosondes, and then we're launching what we call larger engineering balloons here.
Hello, cowboy engineering here. What are you doing?
We attach this to basically the balloon, like right below where we're connecting the balloon to the payload.
Yeah.
And usually we have a little bit more sophisticated weights, but we didn't want to just ship weights to Spain with us. So we took water bottles and filled them with rocks.
I love it.
We have a little bag of like souvenir kind of things, like signed NASA stickers and things like that we're going to send up on the balloon.
This is going up, so you can sign it.
Hey.
You're signing it Eclipse?
Well, I mean, Eclipse place, but I want to show it up.
I thought you were going to say like Henry or something.
Henry was here.
We're now putting you in the balloon though. So.
Yeah. I don't know.
We're going to set up kind of in the middle just because of the wind direction at the moment.
Okay.
So right now the wind's going the wrong way from the forecast.
Okay.
Right? So it's blowing us that way. Which is fine, so we had to be far enough that we don't hit the church.
How strong does the wind have to be for you to hit the church? Like, it's pretty far away, no?
It is, we just have to outclimb it before we get there.
Okay.
So.
It's kind of weird. I feel like it was like one of those things where I'd seen pictures of them, but I didn't realize how much it was just looked like a regular balloon, but just supersized.
On the count of 3. 1, 2, 3.
Amazing. So that launch went absolutely perfectly, and right now our cameras are on their way up to the edge of space.
But about 3,000 kilometers away, NASA's launching another Eclipse mission, one mounted on a 70-year-old Cold War-era bomber plane. They're trying to chase the totality for as long as they can, but surprisingly, this has actually already been attempted. In 1973, the Concorde went Mach 2 and stayed in the totality for 74 minutes. Here on the ground, the longest anyone's going to be able to see the totality is 2 minutes and 18 seconds. And with NASA's jet going at 460 miles per hour, they're going to be able to stay in the totality for just around 3 minutes. It doesn't seem worth it, but they're not just trying to stay in it longer. Compared to a balloon, which is a bit shaky, a jet is much more stable, so it lets them mount much more sensitive equipment so that they can study a very specific part of the sun. Part of the sun that once led to the discovery of a fake element.
On the total eclipse of the 18th of August, 1868, French astronomer Jules Janssen went to India to look at a part of the sun that's normally outshone from observation. The prominences, arcs of glowing gas at the very edge. He put a slit in front of a prism and broke their light into its constituent wavelengths. Out came 5 bright bands. One of them matched no element known on Earth. 2 months later, the English astronomer Norman Lockyer saw the same line. He called it helium, after Helios, the Greek god of the sun. The next year, other scientists used the same method on the hotter corona and found another unexplained band. For 70 years, it was thought to be an element called coronium. But in 1939, it turned out to be iron, so hot that 13 of its electrons had been ripped away. So an eclipse led to discovering both a real element and a fake one. Now, to study the eclipse, Janssen used a slit, but you actually don't have to. So here I've cut out a triangle shape in this cardboard, and we're gonna see the shadow that it casts. You can see there's this projection of light that makes a triangle. Not too surprising. But watch what happens as I slowly move it away from the ground. You'll see that triangle slowly morphs into a circle. I can even take this eclipse shape, which looks like an eclipse when it's close to the ground, but I pull it again and it's always a circle. Here, what are you seeing, brother?
Let me switch the glass. Oh, we're getting like a nice croissant shape, you know?
I think it's called a crescent.
No, a croissant. It's like very thick. Check it out, check it out.
Yeah, no, it's cool. Okay, we take those same cardboard cutouts. Again, here's the one with the triangle. And again, you're seeing a triangle. But look what happens when I move it away. Look, it's a crescent. How cool is that? Okay, and I can do it with another shape. I'm gonna try with this star shape. Which again, close up. What if I move away? This star, also a crescent. How sick is that? You can even do it something like this. With all these little circular holes. Circle, that's a circle. But even quicker, just a bunch of little crescents. That's it, right? Come on. See, when the cardboard is high enough, you're no longer looking at the hole, but a projection of the light source itself. Light travels in straight lines, so a ray leaving the top of the sun has to angle downward to get through the hole. So it lands at the bottom here. The top goes to the bottom, and the left flips to the right. Everything crosses at the hole, and it comes out on the other side reversed. Which means that during an eclipse, the crescents on the ground point the opposite way to the crescents in the sky. All cameras actually work like this, flipping your image. But to get this effect, you need the point to be rather small. It's like a pinhole camera. That's why all the spaces between leaves and a tree are perfect. During an eclipse, they all become crescents. And there's another crazy effect. Watch my hand. The shadows around my fingers are quite fuzzy, but if I turn my hand 90 degrees, those same shadows suddenly become much sharper. As we approach totality, every object has a sharp direction and a soft one, 90 degrees apart. Take one point source of light. On its own, it casts a perfectly sharp shadow. But add a second point, also perfectly sharp, but arriving at a different angle. Now, where the two shadows overlap, you get full darkness. But out at the edges, where only one of them lands, you get half the light. If you do it from more and more points, well, those edges start to stack up into a gradient. And that's what makes the blur. And during an eclipse, you're left with this sliver shape. In the tall direction, it stays roughly the same width as normal. That's why in this direction, you still get blurry shadows. But change your orientation 90 degrees, and now it's much more narrow. So now it's like a point source again. That's why the shadows in this direction are perfectly sharp.
So we're a few minutes from totality, and what we're going to do is we're going to hold up this sheet, and what we're looking for are these long moving shadows. They're sometimes called snake shadows because of how they move.
So you're talking about seconds before totality that you'll see these shadow bands occur. So maybe 20 seconds, 10 seconds before totality. And so you really have to be, looking for them and aware that they're going to exist.
Gosh, I'm a bit stressed about us filming these now.
Oh, you'll be fine. I mean, you're either going to be pronounced or you're going to be able to capture them, or they're going to be so subtle that nobody's going to see them anyway.
Is that it? No, I think there is a little something. Like it's faint. Oh, that's so weird. See, did you see it? Like, it's definitely there.
I don't know. I felt like you were just moving like the sheet.
No, come on. It was there. Like, they are real.
We saw it. It was faint.
There is still some mystery around the shadow bands, but exactly what causes them, there is still some discovery there. And so it's absolutely an open question. Right as you get to the final seconds of light before the eclipse, and you just get, it's a Bailey's beads, where you just get a single point of light or just a few points of light along the limb.
The leading theory is that these narrow beams of light pass through many layers of air of varying temperature and densities. Each of the boundaries between those layers of air refract the light, bending it this way and that. This is actually the same effect that makes starlight twinkle. But if that were the whole story, as you went up through the atmosphere, surely you wouldn't see these shadow bands. Did you hear, because there was an experiment done in Burgos by an army engineer in 1905, in the 1905 eclipse, going up in a hydrogen balloon.
Oh, wow. I hadn't heard that.
Actually looking for shadow bands.
Oh, really?
So they launched these balloons. They've put these big white sheets under the balloons to try and spot it. And then they weren't seeing anything. They're standing at it. And then all of a sudden, someone pointed out they were just everywhere, like on their hands, on the basket, and they saw them everywhere, but not on the white sheet. They were just surrounded by it. But again, someone was already testing it, trying to test it at altitude back in 1905, right here.
That's amazing.
But what's going on there? Is there another explanation?
So there are, the other thing that is coming into effect there was the actual topology of the moon itself. So those different point sources, as they line up and interfere with each other, that's where you get some of those sort of secondary effects that make them more pronounced, because you can imagine it like, you know, in a theater. If you could picture yourself in a theater and you have one spotlight shining, you have one point source. If you had 3 spotlights, you're going to get some interesting sort of overlapping shadows, and that's one of those effects that amplify that shadow bands.
Oh, that's cool.
Yeah, 15 seconds.
Okay, quick, whip the glasses on. Oh my gosh. No. Whoa, that's so strange.
Man, this is so crazy. Unbelievable.
I don't know what I was imagining, but this is so much more insane. Everyone's going wild.
I love this guy. Oh my god, you can see the corona.
And look at that like really bright spot on the left, like sticking out.
It's ethereal.
Is that like a solar flare?
I don't know what the words are. I'm just like, this is cool. Yeah, right? It's the 360. Oh, the 360. Yeah, you're right. There's a 360 sunset.
Oh my goodness!
I love that you're having a good time here, right?
It's incredible. I know you. Where are you from?
Veritasium is the shadow.
Jesus Christ! This guy from Veritasium! This is amazing! It's coming back, it's coming back! Hey, look at the sky, look at the sky!
Unbelievable!
It's made my life. You got me unreasonably fired up.
And then like, whoa! And then that's ring in the sky.
This is sweet. Woo! I've never been this pumped up on a natural event before. My God. Bro, how was that? How'd you feel, man?
It was insane. It was insane, really. I don't know. You can't explain it. Looking at it in person, it is kind of cataclysmic. You gotta cry.
We're up at the crack of dawn, chasing this below.
They did this crazy path and then ended up falling much closer than they thought.
Still probably gonna be at some farmer's field somewhere. Might have to do a little hike to get it. Do we go for it?
I mean, I don't know.
He's going for it.
And then we have our cameras, so that's good.
So this is the one?
Yeah.
Okay, cool.
Oh, there you go.
Something's going.
That's crazy.
That's insane.
That's so cool.
My favorite shots of the shadow are where, yeah, you can just see part of it like receding.
Yeah.
So we had about a 7-hour drive to get here. So we had plenty of time to catch up on podcasts, and we ended up listening to one from today's sponsor, 80,000 Hours. It was about the Fermi paradox and some potential solutions. It was pretty intriguing. If you're into long conversations that dig into big ideas, their podcast is worth checking out. 80,000 Hours is a nonprofit that's built around a simple idea. Your career is about 80,000 hours long. That's a huge chunk of your life, and it's probably your best shot at making a real impact on the world. What I like is they don't just tell you to follow your passion. Their advice is actually evidence-based. It's supported by over a decade of research. Their site's got career guides, deep dives into different paths, and a job board that's full of high-impact roles. And all of it, the podcast, the research, the guides, it's all completely free because they're a nonprofit. They're not trying to sell you anything. So if you're trying to figure out your next step or just curious how to have more impact with your work, head to 80,000hours.org/Veritasium. It'll get you their free career guide, which walks you through what makes for a high-impact career. It might give you some ideas you might not have considered, and it'll help you turn them into an actual plan. It'll also sign you up for their newsletter, so you'll get updates on new research and job opportunities a couple times a month. Thanks to 80,000 Hours for sponsoring this one, and as always, thanks to you for watching.
One last thing, I wanted to thank Astrum, and if you want to learn more about the sun's corona, you can check out their video in the description.
Also, thank you to Exploratorium for letting us link into their live stream.
And of course, these guys, the team from NASA Borealis, for all of their help.
Yeah! So we've taken a bunch of stickers and we flew them to the edge of space. You can see them right here. We're now all signing them. It went to what, 92,000 feet?
Yeah, like 30 kilometers.
Insane. If you guys want your hands on one, we're gonna give them out to our Patreon members. It's totally free, so if you wanna check that out, the link is also in the description.